All right. So shall I intro? Shall I start chatting?
Yeah, so I guess this is session 11. We're going to talk about the builder subpackage and building vectors and matrices.
Yeah, very cool. Um, this will be closely tied to of course, the matrix data structure. And we've talked about this already. There's four fundamental formats: sparse, hypersparse, bitmap, and full. And then there's those by row, those by column. There's the pending updates. There's zombies. There's are there indices out of order or not? I keep track of that. A finished matrix has none of those, no zombies, no pending operations, and it's in order. Because once you wait on the matrix, it's got to be read-only object for some other potentially user thread that's calling GraphBLAS that wants to share that matrix. It has to be uh, waited upon with a materialize or complete. I forget which. There's two kinds of waits. I get them mixed up. Um, one doesn't finish the work, but it flushes the cache so that another thread can pick it up, but and potentially finish the work. But if two threads want to read in parallel, they have to finish it completely for that to happen. Part of this is the build. Build is fundamental to that because I've got a list of pending updates, pending inserts. Those are row, column, value in order, and then I have an operator that tells me which operator do you want to use to smash those together. So build is a fundamental part of the pending operations, like pending and also the wait. If I do, let's see, somewhere in the wait, there's going to be a build. Um, yeah. So the wait calls to the builder as well. And also potentially the hyperhash build, which is something kind of not really the builder, but it is somewhat related. Okay, so let's look at the builder. The fundamental purpose of the builder here um, is these are the four um, user available functions for build, and they take a list of rows, columns, and values, tuples we call them, and then construct and they're user visible data, and then we import that and construct then a GraphBLAS matrix. I actually have two variants of these. Well, matrix and vector, those are basically the same, but I've got build where you give an array of values. I have an extension to the spec that says build, but all the values are equal to the scalar, and there's no duplicate operator to merge duplicates. If there's a duplicate, you just that scalar. The output matrix then is by definition ISO valued. And that's super important because unweighted graphs, right, are very important. So let's look at GRB matrix build first. This is the top level interface, but the builder, in fact, if I do act-l GB builder, you're going to see it in a bunch of places. It's inside the builder. This is the core worker routine. It's inside the concatenate. It's inside import export. It's inside the reduce if I need it. No, that's only the factory because it uses the same set of monoids. Reshape, transpose might need it as well. We talked about the transpose. There's two fundamental forms of transpose, like a bucket sort, where every bucket, you have a matrix by column story transpose into a matrix by row. Every bucket is a row. Okay, so that insertion into those buckets, then if it's a single thread, that leads to a sorted output. But if it's multiple threads, you have to do atomics on the buckets and so forth. I have different kinds of bucket transposes, but you can't do bucket transposes, say, on a hypersparse matrix. There's too many buckets. Um, so the transpose can say, oh, let me just convert it to coordinate form, flip the row and column indices around, rebuild that matrix. So the builder has to be very careful about how it handles the hypersparse case. And as a result, you're going to basically see that that's all I do. I build the hypersparse matrix first, and then I decide, oh, you want to be something else. So these are the what 13, 15 or so 15 different versions of the matrix build function, and unfortunately, there's this proliferation of types, user visible types. So we have the whole suite of bool and float and so forth. But the first thing I do is just simply collapse those into the build, and now I pass in the actual type of of the um, the GraphBLAS type object. So now I have void. Now I just have a single method called build. This does the whole work for the user interface. This method is only called from the user. It itself is not the final core method. That calls the builder, which is then called internally by many methods. Um, so a lot of discussion up at the front. Let me kind of walk through here. The build methods start by building a non-ISO valued matrix, but then I think I check to see if they're ISO valued at the very end, because if they're all the same, suddenly, oh, I can just free the value and do that. There's an important concept in the build called the duplicate operator. What do you do when you have two entries or more entries with the same row and column position? Now the spec says something useful, although not quite complete as it could be. The spec says that this duplicate operator must be associative and commutative, full stop, and it's an operator. It's not a monoid. So that's unfortunate. We don't necessarily know what the monoid identity value is. So that's in one sense the spec got it wrong, I think. It should be passed in as a monoid. That's one. So the spec is sort of straddling in the middle. It's got an binary operator, but it doesn't have an identity value. What? Like, it's going to have an identity value. Please give it to me if I'm going to do an efficient build with a monoid, and knowing the identity value is good for parallelism. But here's the thing: I don't even exploit the binary op associative community. I don't require that. In fact, my spec says I relax that in my implementation. It does not have to be commutative nor associative. And what I guarantee, and there's a reason for this guarantee, I didn't just add this willy-nilly, I added this for a reason. I allow the dupe to be non-associative, non-commutative, and I guarantee that if there are duplicates, like here I've got 4 different duplicates. Is the screen big enough? Can you see this? Is this okay?
Yes,
I
it
can
works
see
for
it.
me.
Okay. Then I apply the operator, like if there's 4 duplicates, I apply the operator 3 times exactly, and I apply it in order. So any one duplicate cannot be summed in parallel then as a result. This gets a sequential summation. So this method does not tolerate it tolerates lots of duplicates, but not lots of duplicates to the same place, like a billion entries of row 3 and column 4. Okay, that would be slow, but that's weird. So that doesn't bother me. And the reason I do this strict order, is because of my pending updates. Because I also use this method to handle those. And those, if you do an assign of a tuple of an entry into a matrix, and you do another sign and another sign, and I can't put them into the matrix data structure at CSR, CSE, and it's not there. So I have to keep up this pile of tuples that are waiting to be inserted. Well, if you do 3 inserts in order, it's the last one that wins, right? It overwrites the first 2. And so that corresponds in here to the second operator. So if this dupe is second, you will get the last value from them all. If it's first, you get the first one, you throw away the rest. And first and second to specify to build is actually pretty handy. There are other coordinate form to compress sparse row or column form algorithms out there. And they typically will say, if there's duplicates, oh, it's the last one. They don't sum them. They don't take the first. They say take the last one, or they have some sort of definition like that. Well, I can do that. I can support that behavior, whereas the spec cannot. So the spec is in a strange middle ground. It's neither a monoid, nor does it even really let me exploit the fact that the operator is commutative associative anyway. Because what the heck am I going to do with a commutative associative operator in parallel if I don't know the identity value? That's ridiculous. That's too hard. So I went the other direction anyway. And now maybe this was a bad decision. I exposed this feature to the user. I could have hidden it internally and not used it, but I thought it's useful to let the user provide second and first to say, just give me the last one. So I did decide to expose it to the, now this, so there's an extension to the spec here that it's in the user guide. It's highlighted in yellow because it's a non-obvious, it's not GXB something. It's just non-obvious behavior of the algorithm when duplicates are present and the operator is not associative or commutative. Okay, so the build method then takes in, it's got the output matrix that already has to be allocated. It's got 3 C arrays, indices, row and column indices, and values. And then the length of those arrays. The operator itself, got the type of the array, that's, C polymorphism here, is a type object, GraphBLAS type. And I have a flag here that says, am I building a matrix or am I building a vector? And that's handy in a very small sense because inside GraphBLAS, there are no vectors anyway. Once I reach the outer layer, a GRB matrix, I'm sorry, a GRB vector is just an n by 1 matrix. And I just cast it right away. So internally, I don't have it. Just and same thing with scalars. They're typically 1 by 1 matrices anyway. That will vary. Actually, there are places where I continue using scalars down deep. So vectors I don't use internally at all. And then is the input, if the C is ISO. This is true if the input is, if the X is going to be ISO valued, in which case it's size 1. So I would use this for the build scalar, just passing in a scalar. Okay. So the standard error handling things, everything's got to be nice. I can't build more than what is nmax. Problem is too large. Let's see. I think that's 2 to the 60. That's a rather big number. I forget why I have nmax there. I think it's, oh yeah, I'll never get that large. Okay, we have to be able to typecast. And now I can know, now I handle the operator. And so this is all handling the user input. So I check to see, is there no operator at all? Now in the spec, you can now pass in dupe being null, which means if there's duplicates, that's an error. And if I find them, if there are duplicates and there's no duplicate operator, I would return an error. Otherwise, if there are no duplicates and dupe operator is null, then I build the matrix, and that's in the spec. So I have another feature which says just to ignore any duplicates altogether. And I think this is a way of saying, give me the second. Give me the last one. If there's multiple duplicates, give me the last one. And it's a place, it's not an actual operator, it's just like a pointer and there's nothing in it. I don't dereference it. It acts like the second operator, but it works for user-defined types because there's no types to this operator. It just tells me to take the last one. Okay, so after things are, okay, I free the content of the C matrix. That's the 5x free. That frees the P, H, Y, BIX arrays, Y being the hyperhash. And then I build the matrix. And then I'm done, practically. This is a really mouthful of a set of parameters here, and I'll walk through these because some of them here, see, those are 3 arrays and their sizes, but I'm not using them. The I, J, and X, but these are passed in as handles. I'm not using it here. And the reason I have this option is I want to be able to do a build that consumes its inputs and also a build that does not consume its inputs. This must be, for the user interface, a build that does not consume its inputs. So I pass it down here. So I have 2 ways of passing these 3 arrays, I, J, and X, to the builder method. And then the builder will take whichever one, does the build, and if it's able to, it can then consume the work. And on return, these arrays are freed, but this one's not using it. So once I build the matrix, it's now in hypersparse format. Then there's an error check to say, well, see, I can successfully build with duplicates if dupe is null. That tells me to essentially ignore the duplicates. That's my old behavior. But the spec added this new behavior, so I have to check for this after the case to see if there were duplicates and dupe was null, then I'm supposed to tell the error, I just built a valid matrix, but I have to throw it away per the spec. Okay. Then if X is not ISO on input, which is the case for GRB builds from Scalar, then it might actually be ISO valued. And this is a rare place where I feel it's worth checking to see explicitly if all the entries in a matrix are the same, and then convert it to an ISO valued format. I don't do that anywhere else by looking at all. I don't think all entries are ISO. I don't think I do that. -L, all entries are ISO. Where do I do this? Oh, that's in the source. Let's see. I guess I do that with the import export. When I import, like copy the tuples in, I guess I must do it there as well. But I don't do this very often. I do it right here in the build, and I must do the import export. And then this is just the method itself of checking to see if it's ISO valued. And so I've built a hypersparse matrix. So I assert here the matrix I built is hypersparse, but you may not want that. Like if you do a build and you expect a sparse matrix, fine. So that's what happens next. This transplant conform appears in many, many algorithms. I have computed a temporary matrix T, and I'm about to give it to the output matrix C. And this transplant conform may do multiple things. It may have to typecast. Like, what if you do a build and you pass in X is double, but your C matrix is float? I have to do the build in double and then cast it to float. That's per the spec. The conform process, and this function is doing 2 things. It's also conforming the matrix. And by that, I mean conforming the data structure. I've got a matrix that's hypersparse T on input. Does it really want to stay that way? Like maybe it should be sparse instead of hypersparse. Or maybe it should be something else. And that conform will make that decision of changing it. But it's way easier to build a hypersparse matrix first than, especially in parallel, than to build, say, some other matrix format directly. Okay, so that is the user interface. And now we get into the builder, which is a beast. It's long. I should have split it up into files. Well, okay, so it's 700 lines of code. It's 1400 lines of C. That's kind of big, isn't it? Yeah, I try not to do that so much, but there you have it. I could have broken it up into smaller methods, but oh well. Okay. So it's a parallel algorithm. And the total time is essentially and sequentially it's E log E. There's no time complexity here. It depends on the dimensions of the matrix. And thus I have to build a hypersparse matrix to satisfy that. There's, as I said, there's two ways to provide inputs to this. You can provide it as a workspace, which I will consume and free. I'll either transplant them into the output matrix and use them, or I'll free them. Or you can pass them in as I input and J input, in which case I won't touch their read only. So JWork, iWork is not only read write, it's actually meant to be, it has to be destroyed or consumed into the output matrix either way. On output, those arrays are null. It's as if they've been freed. No, the user or whatever the caller doesn't own them. They're now inside the graph, the T output T matrix. I'm calling it, I think. What do I call the output matrix here? T. Yeah. Okay. Um, and let's see. Okay, so the interface to this is really a mouthful, and it's not even split into inputs, outputs, input, outputs. It's a mess. Um, but I've got the basic matrix properties, the type, the dimensions, which again, I don't care. I just need to know how, I don't need to know the dimensions. I just need to know how long are each vector and how many vectors do you have in the dimensional space of that matrix. And then I have a flag that says, is it true or is it CSC or not? And so this algorithm is agnostic. And that flag is just used, oh, sorry, I guess it's used and it's just in reporting results. And also in the output matrix, it's set, like when I create it, I set that flag, but otherwise I'm going to build that matrix with those dimensions. Then I have the tuples here as freeable workspace. And then these two flags are useful because it can save me some work. If I know that the input is sorted, that's true. Like I don't have to do a sort. If I know there's no duplicates, then I can skip searching for checking for duplicates, and that saves me some time. Now, if I'm giving input from the user, I have no idea, so those are false. But if I'm using it internally, I'll sometimes know these facts. And then how long are those workspaces if I have them, I guess. I forget what I use that for, but then I have the other inputs, which are read-only. They're const. And then I have the operator, any binary operator, but not index binary op. I've implemented the index binary op. We're getting close to finishing it, getting close to it's working. It took me less time than I thought it would. The type of this matrix, either S work or S input, my burbling, and then this is my Verk space. That's little bitty space that's sitting on the stack. I think I described that before, didn't I? The GB Verk.
In the beginning when we talked about data structures.
Okay, yeah. So Peter, I don't think I described this to you. So let me just rehash what this is. This Verk space is used, and I misspell it on purpose so I can grep for it. It's Werk, right? The German. It's used for small bits of memory space that will fit on the call return stack, basically. And I'd love to use, I used to use just C dynamic arrays, right? You could do stuff like, oh, I just want to have an int64t workspace of size 5 times the number of threads plus 1. Hey, no problem. Yeah, Linux would say great. The Mac would say great. Windows would say fine if you're using the GCC compiler. But if you're using the default Microsoft compiler, this thing it says I don't support ANSI. I don't support C99 for this case. Sorry. That's so tiny it should fit just fine. Well, no, it doesn't. So I had to do my own hack. It's kind of unfortunate. I have to port to a cruddy compiler. All right, so determine how many threads to use. I have this concept of this context object. which is engaged. I don't know if I described that. Did I describe the context? I don't know if I did or not.
I don't think we've covered context yet.
Okay. It's basically data that gets shelved away in thread private TLS, thread local storage, private to each user thread. Okay. And I don't use it inside my parallel regions. And that space then is where I can put things like, well, how many OpenMP threads does this user thread wish to use inside its calls to GraphBLAS? This is an unfortunate thing that ought to have been in the BLAS itself, the dense BLAS, because you're calling them in parallel. The MKL has this, I think OpenBLAS has an option, but they're different. They're not portable. So it's really a mess for the BLAS spec. And so I have it's not in the GraphBLAS spec either, but I've implemented it, and I've implemented it in such a way that it doesn't change the API of any GraphBLAS call. It just changes the this thread local source. So that tells me that little place where I can put like how many threads do you want to use, how what's the chunk size, which is a work balance, a load, not a load balancing thing. I think the chunk size default is 64K. It basically says if I've got 128K of work to do, I'll use at most 2 threads. 64K is kind of small, but that's my default. So I'll if I'm solving a tiny problem, I'll just use a single thread. If I'm solving a medium-sized problem, I won't necessarily use all the threads. So this is all the threads available to it. Like I'll ask how many do I have, and then I'll available and what's the chunk size, and now I know the number of threads to use. Because I needed to get some workspace for every thread, some amount of integer space per thread. And the first thing I do is to partition the tuples. This is a really simple parallelism. It's just a static partitioning. I think it's in the slice folder, GB eSlice. eSlice is super simple there. Just this GB part is just give me the TID part of E item. So it's basically you know the fraction 1 over like TID divided by n task times E, something like that. Floor and ceiling appropriately. So and I just use this thing in a lot of places. So I split up the work, and so every node knows where every thread knows where it's starting and finishing. And so this will create the first tuple is done by the TID slice, and T means task, not thread. Oh, I have threads. Okay, it's the number of threads. Here it's the number of tasks. I guess I have 1 task per thread here. So if I have 24 threads, I'll have 24 tasks. Some other places I'll do it differently. I'll have more tasks than threads to get some work balancing. And then I want to keep track of the number of unique vectors in that slice, and also the number of entries in that slice after removing duplicates. So currently there's none. It's empty space. All this is a sentinel value. It's not initialized fully yet. Okay. What are the different steps? There's 5 different parallel regions. First thing I do is if need be, I copy the user input into space I can modify. And that's of course expensive. And so if I'm doing it in place, I don't have to do that. The next thing I do is the sort. So so now the user input I don't use anymore. So where is it? Input. The input arrays, once I'm done with them here, let's see, where do I'll finish at some point. I'll never use them again. This is just comments. So I will, at some point, like this is just comments here. This is doing error checking. So it's checking only inputs. If it's workspace, It's already been checked. It's not needs to be checked. Because I will assert that it's valid on input. So step one is doing the copy and sanitize. And so if if I don't have the workspace on input, I have to allocate it because I'm going to make a copy of the input tuples and also check if they're valid, check if the entries are valid. And let's see, will I do the sort here yet? I don't think I do get the sort. I do look for duplicates, but I'm not going to find them all. However, this is useful to do because as I'm making this copy, I can check to see if the tuples are also sorted. And if they're sorted, then that flag, no duplicates found, is valid. Okay. And then I can skip as I'm making the copy, I realize, oh, this is nice input. It's sorted with no duplicates, and that saves me time. And I don't have to do another pass. Okay, so every thread basically goes through and does the copy of the of its space, and it also does some simple analysis and some error handling. It detects, for example, if it's out of range. If it's out of range, then this thread finishes. The other threads don't yet know that. So that this has to be every thread might find, or some threads might find no errors, and some will. So I have to coalesce those results together. I can check to see if by looking at the row and column indices if the inputs are already sorted, and I can check to see if there's any duplicates. Like if you have pairs of indices are right next to each other, they're sorted, but I can now see if they're duplicates. And I also count the number of unique vectors I've seen. Now this is also not going to be valid unless the input is also sorted. If J is sorted on input. So I'm doing some really simple analysis here that I may throw away. So at the end of the parallel region, I check to see if I have an error. If I have an error, I've got to report that. And the error message I report, you notice, is kind of funny. It's like, are you talking about rows or columns? Well, yes. You see, I have already, if I'm building a compressed sparse column matrix, then I's are rows and J's are column. If I'm building a compressed sparse row matrix, it's reversed. And the algorithm is the same, so why write two algorithms? But when I report an error back to the caller, I have to say, oh, this is a row and this is a column, and it's bad. It's out of bounds, say. And so I don't want to have that flipped. So I handle the flip, algorithmically, internally, it's just the same algorithm. So I don't bother to, I just, J is the vector, and I is the index inside that vector. It's the jth vector of the matrix. And well, is the jth vector a row index? Well, it is if it's CSR. So that's what's happening with this. And the same thing with the number of rows and the number of columns. I don't even know the dimension of the matrix. I just know if it's stored by column, I just know the vector dimension, which is the number of vectors, is equal to the number of columns, and the vector length is equal to the number of rows. But if it's reversed, that's just reversed. So I have these 4 ternaries to handle that. So that's the error handling. And then I know that I've also validly computed the number of this statistic if I know the inputs sorted in duplicates. Okay. And now I can grab the create the JWork if I need to, but I don't necessarily have to create it. I've copied over the row indices. I've not copied over the column indices. Where is this? Yeah, JWork is done later because I might not need to build it. Because if it's sorted, whoops, if I don't have the J indices, I don't need them. If I'm building a vector, J is not built. And if I don't need to sort, I can use J work as J input, and then we're fine. And then I don't have to destroy it. I can use it in place. What I'm trying to do in all of this is I want to support fast builds and it's a huge difference, like order 10x speed up. If I can avoid duplicates, building, construction, and avoid sorting, it's easily 10x performance difference. And there's a lot of places inside my code where I know this to be true. There's like, I know I'm not out of range. There's things I can do. But if the user input wants to have this availability to get this good performance, what if the user is able to give me a set of tuples that are in order with no duplicates? Well, I can very quickly check that right here. And I have to make a copy anyway, because I don't know. But as I'm making this copy, I can do these checks, and then later on, it saves me a ton of time. Okay, if the input is a matrix, then I have to check both I and J input. If it's a vector, this algorithm becomes simpler, and I just have to check the row indices if I'm only having one input. And then if there's an error, the error looks of course different. Okay, so that's step one. I've made a copy of the input tuples. I've done some basic sanity checks. I now know that everything's in range. I know that it might be sorted, and if so, I know that I will know if there's duplicates or not, and I'll know other things too, like other statistics about the tuples. So now I sort them if I need to. But if now I'll know, like a known sorted, I can say, oh, well, now I know it's sorted. Yay. So suddenly, known sorted is an input flag. I may know it's sorted on input already, but if I check, that would only be true for a non-user input. But if I find that it's known sorted from this phase, then I can exploit this later on. So, but now is the general case. Like I don't know it's sorted. And I just simply sort all the tuples in ascending order. So I have to create, and this is I have to number the tuples, okay, because I need the sort to be stable. I need ij and k value, and k is not the kth vector of the matrix. It's just the kth tuple. I could have called it something else, I guess. Because of other places, I tend to use the letter K for lots of different things. And here I'm using it for the kth tuple. And so the sort will be stable, even if I don't have a stable sort, because now there's no duplicates. And I do this with a parallel merge sort. And that's another algorithm, if need be. And whether it's a pair of tuples or three values. You see, one advantage of this, then it's not sorting the numerical values yet. I'm just sorting these indices, which then if I look at a tuple, I can know what's your numerical value. Oh, you're the third tuple of the input. Oh, I just get it from position 3. That tuple may have been moved around in this array, but I know where its value is. So this is type agnostic. I'm not sorting the data types as I'm doing a sort, just the integers. It's a sorting a pair of integers or sorting a tuple as three integer arrays. And I can't do this. I had to do this as 3 separate arrays because the inputs are 2 separate arrays. And so I have to have different arrays. Okay. So now the merge is done. Now I have to do some more analysis, potentially. So if where is it? If I know there's no duplicates, there's no duplicates, I only have to check for the counting. Basically now it's sorted. It's easier. I just have a debug code here that looks to say, oh, there's no duplicates. And now the tuples are sorted in the workspace. And now I need to count Here, like if it's a single vector, everyone appears in the same output vector. But if um, it's a matrix, and if I haven't computed this result above, then now that it's sorted, now I can compute this. I can say, well, how many different vectors of the output do I own? See, I'm got to build a hypersparse matrix. So I got to know this thread owns the 10th to the 20th vector of the output. And then the next thread might own the 21st to the 24th, and so forth. Now, a thread's going to own, let's see, how does this, there's a, if you're in the middle of a vector, I think I give that vector, I count it in one or the other. I forget where I count it. If I'm also looking for duplicates and counting, then it's a multiple phase. Here I have to, if I find a duplicate, now they're next to each other. And now I can count them, and I can flag it as the dead. iWork is flagged as -1 to flag this particular entry as a duplicate. And I count up how many duplicates I have, and then how many, and I forget what I do. Oh, yeah, because I got to know where to put my stuff. This is the number of things I own, number of entries I own in the output. And these are the number of vectors I own in the output for this particular I being for a particular thread TID. Okay, then I've got to do some cumulative sums so everyone knows what parts of the output matrix they own. So now I'm ready to allocate the output matrix. And here it is. It's always hypersparse. And it is currently, the contents are empty, I think, with this initializer. I didn't give it the total number of entries. TNZ is not passed in here. I now know the total entries in the final matrix. And which could be smaller. You know, this is how, now I know the exact total global duplicates that are going to be removed. So I've allocated the matrix. That only allocates the P and the H array, but they're not, they're malloc. That's what this flag says. And then they are, so the contents are not defined, but the I and the X array are not allocated. Okay, and that's, I like to do this sort of thing here at the end. So the only the PH arrays appear and EIX are not appear. And I'm not building a bitmap matrix. I may in the end have a bitmap matrix. After I build the thing, I might say this is 50% non-zero, make it bitmap. I could have done a bitmap build to begin with. That would have been a different algorithm, and I don't bother to do that. Okay, so now I know every thread knows how big of a piece of their output matrix. Now I need to do a kind of cum sum for every to build these two arrays, the TH and the TP array. We've got to know how many. Basically, it's basically a cum sum across. Vectors are simple. If I have no duplicates, that's simple. We know. We just get the tuple, and if I own it, let's see, JLess and JLast. What does this mean? Oh, this means you have a start of a new vector. If so, it's mine, and I'll put it there in the list. So very simple array. There's no reductions here needed for this. If duplicates do appear, I have to check just to not do this for a duplicate, just skip over that. Otherwise, these two codes are just, these two functions are just the same. Okay, so now I've built the TH and TP array. And when I'm done constructing a matrix, you'll often see this happening. This just means do this line of code, right? This is an array of size n plus 1, where n is the number of vectors in the data structure. So TP of n is the total number of entries in the matrix. And now the magic. Now it's magic. This means that the P and H array are valid. That's what the magic means. This magic thing in the data structure for a matrix is used to detect corrupt and invalid and not initialized objects. And that's required by the spec. So I had to put in the magic. Okay, now that I've constructed so I haven't summed the duplicates yet, but I've constructed I've sorted the tuples. So I have the row indices. I've not deleted the duplicates yet, but at this point, I no longer need J. J is now in monotonically ascending order. It's like the first vector, the second vector, the third vector, the fourth vector. And I know where all the vectors start anyway. Or I guess, let's see, what do I know? I don't need them anymore. I guess I store, what do I store? Let's see, why do I not need to know? I guess I don't need to know the column indices anymore in the J, so I don't need it. So I free it because I'm going to allocate more space later on. This is all symbolic. There's no numerical work done yet at all. But I've not yet allocated the I and X ray of the output matrix. So now I'm ready to do that. And I guess I don't need J anymore. I forget exactly why, but obviously I don't need it, so I free it. So now I'm ready to allocate the output matrix. And if no duplicates exist, then, well, I will just shrink the space of the input workspace. No, I'm sorry. What do I do here? No, I just transplant it. Yeah, there we go. If duplicates, yeah, if no duplicates exist, then the row indice array has just been sorted in place. There's no need to allocate it. I just use it as is. However, I may have less space, more space, I'm sorry, than I need. This is the actual size of the iWorkspace, and this is the size that I actually need. And so if it's smaller, I shrink its size with a realloc. And I have an assertion here that it's okay. This is, I hate the C realloc API. If it fails, it returns a null pointer. And it leaves the space allocated. That is so confusing. If a realloc fails and it's shrinking, well, fine. I don't care. Just the pointer doesn't have to change. Just you failed to shrink it. So this can't fail. So I assert that it worked okay because of this case. So I transplanted in. And you notice I don't typically put two lines of code on the same space like this. Okay. But I'll do this in here because I think of this as a single execution. It's a copy of a pointer, but like a rich pointer. It's an annotated pointer. It's a pointer that has it's not just a pointer, but it's also the size of the thing to which that pointer points. There's two things. I could have put that inside a single struct. Some people do that. I didn't. I have two separate things for that. And the same is true for the thing I'm transplanting. So this is a transplant moves over these two values. Okay, if duplicates exist, then I have to allocate new space and I have to then free the workspace. I'm not going to try to sum the duplicates up in place. That's difficult. If it was sequential, I could just squeeze it. but in parallel, that's difficult. So I allocate new space, even if the workspace is to be destroyed anyway, I'm going to make a copy out of place of the matrix without the duplicates. Okay, so now things are sorted. And I need to do the assembly of the space into built-in workers, or I have 4 generic workers, which are going to use mem copies. And I probably use a JIT here somewhere too, I think. Do I use a JIT? I might not use a JIT. Oh yeah, I use a JIT. Cool. That's right. Where is it? Where was I? Here. So I could have made this a separate function. I surely should have. This is already, I'm 68% through the code, and that's a mouthful. I could break this up easily into 2 separate functions at this line here, at least. Even step 5 phases. I could do phase 1 through phase 5. That would make a lot more sense, but I didn't. So let's see, let me just, this is the input to this phase. I don't need J anymore. I have the row index, I have the K value of the tuple, which is if it's the third tuple in the matrix, K is equal to 3. And I'm sorry, third tuple in this list of the original input. So I know where to find the numerical value, which is Sx of K. Sx is the numerical array. That comes from, that X array comes from either the workspace or the user's input, depending. And it's not used until way down. It's not used until way down, finally here. It's commented but not used. So finally, so these are the things I'm building. I have a list of these. But I also have in this list, so I have a list of, there's 3 arrays. There's the I array, the K work array, and the Sx of K, if you will. It's index, it has to be mapped. And I don't have JF for it, because I don't need it anymore. If the thing's a duplicate, there's a -1 for its row index. And that just means it's a duplicate of the ones before it somewhere, which is going to be recorded in the first one's not set to -1. So the duplicates are going to be looking for these, the duplicate code is going to be looking for these -1s, and that will be the region. It'll have the first one, which has the row index, and then all the -1s after that are the duplicates for that one entry. But the K values will all be different because they come from different input tuples. So that'll be the numerical values I need to mash together into the output. Now, if the input dupe is null, this is my old behavior. I'm still using my old behavior. If you pass in null for the dupe operator, that tells me that it's a second operator. And I'm going to either look it up or build it, construct an operator on the fly. And it's in binary operator, GB binop second. Okay, so I'm actually potentially creating a new operator, because the second operator is fine for built-in types. But what about a user-defined? There's no second UDT, which would be kind of handy, wouldn't it? It's just a mem copy of a certain size of bytes, which would vary depending on the type. It'd be an operator whose input-output types would only depend upon, they would be, runtime morphable. Like you pass in a Gaussian integer, you get out a Gaussian integer. You pass in an array of size 64, you get an array of size 64. Okay, it's just a mem copy. And but I just need to know I just need to then set the actual type for it. So I actually create a new operator, but this operator has to be interpreted as a mem copy deeper in my code where I'm using this operator. This operator will not be given back to the user. It's going to be destroyed. This operator is going to be used to assemble these duplicates. This particular operator then has the second opcode. This is an enum value. And it has, this is the function pointer. It's null. But this means I can't call that function because it's a function. There's no size of type passed to that function signature, which is unfortunate, but that's it. And so it can't just do a mem copy, the function. So I have to do the mem copy myself. I can't call it through the function pointer. So I put in a null function pointer. And wherever I see this operator, I have to have a special cases. Is if I ever want the function pointer, I have to say, oh no, I'm not going to use the function pointer for that one. I have to do this mem copy with the size of that type, whatever type it is I'm working on. It works. It makes for some slightly awkward special cases later on, and I explain it to death here. I do the same thing for the first operator because I need it in the reduced to vector. Did I describe the reduced to vector? I don't think I did. You remember?
I'm not positive either.
Taking a matrix and reducing it to a vector. That's just a matrix vector multiply using a special summary ring, and that's all I do. It's a can be a very complex algorithm. It's 15,000 lines of code to do matrix multiply. So I don't want to have another 5,000 lines of code to do a good reduced to vector. I'll just convert it into MXV and I'm done with a summary ring. And that works great. And I have to do the same thing, but with the first operator, not the second. So I have another function called gb_binop first, I think. Don't I? Oh, I thought I did. I guess I don't have a separate function, but I do it, that thing, inside the reduced to vector. Okay. So if dup is null, I replace it with the corresponding duplicate second operator. Okay. Now I'm getting ready to fire up the factory. And I don't think, yeah, you've seen the idea of the switch factory and the workers for the switch factory. So it's my templating in C. I call it the switch, I call it the factories. I'm getting out the operator and I'm getting its sizes and its type codes and I'm about to go in and decide, oh, well, there's actually no work to do. Great, it's a mem copy. It's literally, let's see, where's the mem copy? Yeah, this is not even a mem copy. This is the special case of I can just copy the values into the final output matrix as is without moving them around at all. If I don't have to typecast and if they're sorted in the appropriate order and there's no duplicates, which maybe now I know for sure if there's duplicates or not. So copy S into T is a very powerful thing to know. But if I'm copying the S array into the T array directly, but S is just the workspace, then it's just an order one move. It's free. And so this makes a build from the user's perspective extremely fast. You see, if they give me a list of row indices and column indices, and they're in, say, building a CSC matrix, and the J's are all right in order. It's all 0, 0, 0, 0, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, and so forth. And the row indices are all sorted. Then I've already have with just do a check, essentially is all I've done, not moved any data around. I've just looked over to detect that condition. And I I don't even, if it's the input array is a workspace, I don't even have to copy the data. I just have to verify that it's sorted. And then if it's no duplicates and sorted, then the workspace, the S workspace could just be slapped right in, order one time. So greased lightning. This is the greased lightning case. Otherwise, okay, I have to make a copy. I have to allocate the output values. And it's all void at this point. The types are not yet constructed yet. But if I can just, now I still can exploit the copy. If it's a copy, I do a parallel mem copy. I have to actually move the data, not just transplant it. And GB mem copy is itself a mem copy, but it's parallel. It's in there somewhere in the code. It's pretty simple, just a chunks of mem copy. Okay. If there's no typecasting, then I have to call the worker. Okay, and I have something called the build factory and a JIT for that, for this condition. And otherwise a generic kernel. And if there is, let's see, if there is typecasting, the workers are a little bit different. I have to get function pointers potentially. And this is the generic code down here. What's happening? Where's the factory? Oh, I know why. I know why. Okay, here we go. Sorry. If there's no typecasting, you are able to use factory kernels, the built-in kernels. If there's typecasting, sorry, it's going to be either JIT or generic. So the factory kernels are in here, factory kernels, and I think they're BLDs. Yeah, these are all of my builders of the operators and their types. So say you're doing plus FP32. This means if you see a duplicate, sum it with FP32 plus. So here's the operator to do the duplicate, plus equals. Here's the operator assignment expression to do a copy, build dupe and build copy. And these are the different arrays and the different data types, and they're all the same. So here's my method. It's got a name that's been constructed, and it's got this is a templated file, and it's got its inputs, and then it's got the build template. And this build template you'll see all over the place here as well. So if I look for GB build template, you'll see it in many places. GB build template. This is my algorithm, not without the, no, whoops, templater. Okay, it's used in all these factory kernels, but then it's in temp. Sorry, this is test coverage. Ignore that. It's then used inside the JIT as well, and it's also used inside this code that we're looking at. And then it's test coverage. That's something you can ignore. Okay. So I guess I have, how many of these workers do I have? A bunch. And I've also got first and second, which are really important. So if you want to say build a float matrix with the second operator, well, this is how you handle the duplicates, and this is how you handle copy. It's the same operator, right? That's what second is. Just, it's not a plus equals. You come across the next thing, you just slap it in there. So the algorithm then is very the algorithm just uses that macro to know what operator to use. This is this templatized method here. If the output is ISO valued, then I set this pound define flag, and this tells the template that don't touch the numerical values. They're done right here with a single scalar mem copy. Let's look at the build template itself. Let's go back to the source builder. So now I go into the templates. Now templates are sometimes entire functions with ahead, with the function call block at the top. But this one is not. Many of my templates are just blocks of code that then have to be embedded in a function. It just starts with a curly bracket. That's it. It's only 113 lines of code. And there's two versions, one with duplicates and one without. First one is without duplicates, and the next one is without. The first one is really simple, but let's look at both. So basically then the ISO value is one case. So this is just building the pattern. It just has to delete the duplicates. That's all it has to do. So it's very simple. The ISO build here actually then does nothing. If there's no duplicates, there's nothing to do because I'm just destroying the duplicate row indices. So if ISO build is true, nothing to do. Otherwise, if I have duplicates, I guess down here, ISO build can skip over the numerical part. Okay, so the algorithm, I guess I could describe the algorithm here. This is important here. It's not in place. Okay, it's out of place. That's important because it's parallel. So you have a thread that owns some of the input tuples, and it knows in the input, like here's my input, and there's some duplicates around in the matrix, and so its output is going to go here in this region. So I might have 1,000,000 tuples that this thread owns between 2 to 3, position 1,000,000 to position 2,000,000, say 1,000,000 tuples. And on output, maybe there's only 500,000, and it's in a different location as well. So I know all of that information. I've already done that pre-analysis here to know where do they go. And now this job, the job of this particular thread, and I do actually have one thread per task, and it's statically scheduled. Sometimes this thing will be tasks, not threads, and I'll use a dynamic schedule to do work balancing. I didn't need to do that for this. This defines the task, TID. It says, how much do I own? Well, where is my output go, my TNZ? That tells me where am I putting my output. So as I'm going to do, my TNZ is going to increment, and this will be where my stuff goes to. My next tuple is going to go from the input to the output. And where am I starting and finishing in the input matrix? Maybe I should do let's see. This is super simple. This is just a either copy, which I probably could have done this as a mem copy, but it's a typecast as well, potentially. Or it is just move the tuples around. Like if it's sorted, but with no duplicates, then it's just apply the sort. K-work is there's a permutation of the sort to get the sorted tuples. If, on the other hand, there's duplicates, I've got to do more. Okay. So this gives me my output place. This is my input place. And then I need to know, well, do I own all of my input? So here's the thing. The duplicate operator can only be applied by a single thread all across a set of duplicates. I've not yet accounted for the fact that this thread may only have some of the duplicates of a particular entry. At the beginning and at the end, I could trail off. So what do? What I do here is as I say, well, look, thread, if your first row index is -1, then you're just going to skip it. Let the guy to your left do it. So it's handled by and so then at the end of your ownership, if you see an entry, maybe it's not a duplicate. Maybe the next one's a duplicate, but you're just going to keep looking into your neighbor to the right to see, hey neighbor, do you start with a -1? Oh, that's mine. I take it. I do that one. That's the definition of the ownership of who's doing what. And so this is skipping over then the things you don't own. Because implicitly, since it's a -1, it's a duplicate of the tuple owned by the thread to your left. So you're not going to do that. Of course, if TID is 0, this is not going to happen. But this skips over. Then finally, we can go through all the remaining. And now if I see a -1, I do it. And so now at this phase in the code, although here I work, and I have this is very useful because the algorithm is kind of subtle. Well, once you see it, it's not too bad, but I like to do this kind of thing. I'll put assertions in my code and it tells me what's going on. I realize, oh, yes, of course. At this point in the code, I forget the -1s at the beginning. We skipped over there, but there's still going to be -1s inside. Well, but I won't see it here. What this means is I will now discover the first row index of the first entry in potentially a sequence of duplicates. Those duplicates have been sorted in a stable sort, so they still appear in the proper ascending order. So I can apply the duplicate operator in order and I get the right result. But at this point in time, I know I'm either don't have a duplicate or I have the first of all the duplicates for this entry. That's what this assertion is telling me. The row index is greater than or equal to 0. Okay, now I got to know, and so ITOBuild will normally be false or not defined. So I'm doing the numerical work. And so now I got to know, okay, where does this, where's the number? I got to know where the numerical value is of this duplicate and also the following ones. And so that's what this line of code does. So I grab and so I grab the tuple. Now I like to put when I have a macro that's super obscure, right? That's the downside of C templating. You have a macro for everything. GB build copy. What the heck does that do? Oh, right, that's doing this. So if I was writing this in C++, right, I would just write that, right? I'm taking the kth value of the S array and sticking it into my T and Z position of the T array and typecasting it if necessary. And the build copy will do that. It'll do that. And if you looked at some of these JIT macro headers, JIT headers, you'll see some cases the build copy macro will have a typecast in it. Or actually, you'll see it down here in this code too, the generic case. So now I own, this is your row index. So this is the final output row index for this tuple. But now I got to eat all the duplicates if there are any. So what I do is then I say, well, let's look at the next one. And we don't want to be past the end of the array, of course. But let's look, I'm at position T. Let's look at T plus 1 to see if you're negative, and if so, increment T. So I'm looking to the right, and I stop the moment I see that the next one is, oh, you're unique. So I could meander into my neighbor's start of his tuples, but my neighbor is going to skip those here. And if I find such a tuple, then that's a duplicate, and so I can do the numerical assembly. I don't need to save the row index because they'll all have the same row index. They're duplicates. But I do have to go get the value. And you notice here, I have to get the value. I've got to get the position, which is the position K of the input array, which is now called SX, which could be the work array. It could be an input array. But its position is given by the K work array that's been potentially sorted and modified. But I do have a check to see if K-work is null, skip it. So if K-work is null, I think what happens is if I realize there's no sorting going on, I free K-work. It's initially null. I allocate it. And if later on I decide, where is it? I look at it somewhere. Oh, where do I pass in K-work null? Well, somewhere K-work can be null. It means just identity. I guess the ISO case. Well, anyway, I'm not sure. I can't remember why K-work could be null. And then I can't remember. Then I use the operator. I use the dupe operator. So this is the copy of the first entry, followed by all the applications to dupe. And so what this loop is doing then is it's doing where was it? It's doing this. It's making the first copy, not using the operator, because I don't have the identity value for this operator anyway. I can't set T to be the identity and then use the operator because I don't have the identity value anyway, which on the GPU is going to be an issue actually. So I'll use the dupe operator 3 times. If I have a initial entry is copied and the subsequent ones are the dupe operators applied. And that handles one output tuple, and then just repeat for all the tuples I own. You notice this as I'm incrementing this T, you notice that's the same T here, right? You just march ahead, assemble those duplicates. The outer loop then is going to start at the next place where there's some work to do. You see how that assertion now tells us the loop invariant as to why that works. That assertion is actually very profoundly important right there. It kind of tells you how this whole algorithm works. Okay, and so the GPU is going to look very different from this. We talked about the GPU build last Friday with in my CUDA code session that I think Peter, I think you were there, right? Weren't you?
Yes.
Yes.
Well, I mean,
that's
last
right.
Friday was HPEC, so it was 2 weeks ago.
Oh, last Friday. Oh, actually, Joe and I met on Friday anyway. Sorry, we should have. Yeah, because
Oh, okay.
for about an hour we talked about it a little bit, some more. We actually decided to meet anyway because I couldn't remember if we had canceled or not, so I hopped on Zoom. And then Joe was there. He said, "Well, I don't remember if we canceled or not." I said, "Oh, well, we're here. Let's chat." So it was kind of like I thought it was canceled too, and I thought, well, maybe I forgot to tell Joe. And so we just chatted for a bit. I think we talked a little bit about the build. So sorry, we didn't intentionally mean to leave you out. All right, so that is, let's see. So now I've done oh, I'm not done yet. I've got the factory or the ISO case, which doesn't touch the numerical values. It just munges all the duplicates. It does the factory kernel with this big switch case. And this is a factory GB build factory. These are this is a switch case for all of the built-in methods. All the min, all the max, and so forth. This macro is constructed here. It tells me how to call the thing. So I'm building this switch case right here for the factory. So I have a very strict kind of rule for doing this. I always first say, define the worker for the switch factory, launch the switch factory. And if you look for, if you do, let's see, cd source ack switch factory, you'll see that actually just looks for the switch factory. There, it's like everywhere. Define the worker, launch it. Define the worker, launch it. I'm very consistent, exceedingly consistent with this code style. Because it's weird. You know, you don't want to see it in weird ways twice. I admit this is weird way to code, I have to say. But how else am I supposed to do it, right? It's not C++, it's C. And I have all these cases I have to handle, so it's a switch case. Okay, what if there's no factory? Ah, well then I just call the JIT. So, and we talked about the JITifier. The build JIT it encodes the problem, and I could walk you through, I don't know, should I walk quickly what the enumerification of the build is? That might be kind of useful. JIT wrappers. So these are all my JIT wrappers. GB build, I have a build JIT, okay. I encodify the build. I try to look it up in the hash table, and if not, compile it, and then I call the kernel. And encodify build is going to be passed in an operator. It's got a kernel code and two different types. And so if I look for the JITifier files, let's see, GB encodify build, here we go. So what's the encodified build? I have to output the encoding and the suffix if it's user defined with the name. I have to tack on the name of the functions and the name of the types. And it's pretty simple, I guess. If the operator can't be JITted, I return a code that says I can't do it. I enumify the problem, and then I can tack on the suffix, and I get the hash. So the enumify build has to create the enum, the bit field that gives you the code. So here's the output, the build code. This is unique encoding of all combinations, and I forget how big it is. It's 28 bits. So there's 2 to the 28 builds I could do for the JIT, not counting different user-defined operators. That's unlimited number. So to do this, actually, it's very simple. All I have to do is encode the operator, I guess, and the types of the input-output matrix. I simplify Boolean operators, and then I enumerate the binary operator, and I'm done. There's really nothing else to do. So it's a very simple encoding. I have to do, it takes me 5 hexadecimal digits to encode an operator. 2 hex digits, 8 bits to encode the operator. So I have an enum for every operator, and there's 254 of them at most. And I have the type codes, there's 14 of them. 1 code for all user-defined types. So when I'm JITting a user-defined type, the Z code will be, I don't know, 14 or something like that, or maybe it's 0 for user-defined, I forget which. But then to know which user-defined type it is, I have to see the suffix, because the name of that type, that's the suffix of the method. And you can see that over here in the cache, SuiteSparse GRB 9.4, which doesn't exist yet, but I'm working on it. I've got here half a dozen kernels, and you notice what I've got here, by the way. Let's see, I've got, I don't have a build, I guess, but I have some fun stuff here. But the type codes are, I think this is going to be a, what's the type code of this? This is a user-defined object, user-defined data, because it's a index binary op subring. The monoid is working on this tuple, which has a value and a row index inside of it. So it's not indexed, but it has an index inside the data type. The multiplicative operator is called make FP64, and that is going to be an index binary op. This is not build anymore. Index binary op that outputs a tuple and takes in a double in its position, and it just produces the position and the value. And then the max is going to do the max of two tuples. So if there's a tie on the values, take the tuple with the smallest row index, say. And so that gives you argmax, or arg, I guess this is arg. Yeah, this is argmax. It's kind of cool. But see, this code here is going into, you know, it's some of these bits. This is not a build. I don't have a build, but anyway, it takes me 4 bits to encode a type. I've up to 5 different types, which is a lot because the dupe operator is not necessarily a monoid with one type. Okay, so that's the JIT. If I don't have the JIT, I've got to do the generic. And now the generic says, well, there's no typecasting in this instance. So in this case, the copy is just a mem copy, and the dupe is just it's either nothing. If it's the op is second, there's nothing to do. I skip it. If the dupe is another operator, then I have to call it through the function pointer. But with no typecasting at all. If there's typecasting, it gets really nasty. I can do it typecasting with the JIT now, but not with the factory kernel. So you don't see the factory kernel here. The generic kernel is an ugly beast because these 5 types, everything has to be cast to everything. So applying the dupe operator, it's got its 3 types. The input-output matrices have their own types. So you just got to be able to typecast everything to everything practically. And so the let's see, which is this doing? This is with typecasting. Oh, this is easy. If the operator is second, it's just skip that. But if there's typecasting, I have to get the value of S, cast it to the value of Y. I have to get the value of T, cast it to the type of X. I have to apply the operator with a function pointer, and then I have to put the result back into T and type it back from Z back to X. So cast Z back to T, sorry. So S to Y, T to X, apply the operator, and then do cast Z to T. It's just an ugly thing. So I guess I need 4. Wait, cast. I guess I need 4 different typecasts. Cast S to T. Do I even need that? Where do I use cast S to T? Oh, yeah, that's in the cop for the copy operator. Yeah. So it's crazy, all the typecasting that has to happen. So this dupe right here, I mean, look what that's done. That's a massive macro. Template. Where am I? Oh, builder. CD template. Yeah, here we go. That build dupe is right there. That's what it's doing. Typecasting as needed with up to 5 different types. And that's a lot of work, but there you have it. So that's it. One thing I know that's really cool, because of the way I've sorted the tuples, I know my indices are in order now. So jumbled is false. And now I've built a matrix. I assert that it's okay. When I have debug turned on, and I assert that the matrix is hypersparse. And the builder is done. So that's what it's doing. It is a beast. It's big. And I use it in many other places, not just here. I think I already described the rest of this here. Let's see, what else? I've not described, it's 11:45. I'm not I haven't described the conform process before, have I? Transplant conform?
Nope.
Okay. Oh, the hyperhash build. I've not described that. Have I described the hyperhash?
It's sort of from a high level. I guess you're kind of using it as an index to look up.
It's okay. So the hyperhash, I don't know if we have time to talk about the hyperhash. It's 11:46. Maybe we should make this another day. The
Yeah, we can
hyperhash
put
is
that on the
important.
list.
Yeah, we should make this. Now that you've seen build, you'll know how I do the hyperhash. Basically, the short answer is this. What is the hyperlist? The AH array. You do J equals AH of K. If I have the kth vector, its name is J. What if I want to do the inverse of that? I can do it in one of two ways. Like given a J, find it in the hyperlist. Well, that's either a binary search. Ooh, that's expensive. Or I can have already hashed all the names into a bunch of buckets, and I can take the one I'm looking for, hash its name, look through the bucket. If there's duplicates, there's lots of things in that hash bucket with collisions, and find it. Those set of buckets, they're not changing dynamically. That's just a CSR matrix, one bucket per row. So I just use a GraphBLAS matrix as the set of hash tables. Why not? One less data structure. That's the hyperhash. But how do I construct it? With builder, hyperhash build. It calls builder on the hyperlist.
And are there situations where the hyperhash is thrown away and you sort of rebuild it as needed?
Yes, there's cases where it's not even built at all. Like if I have a hypersparse matrix with fewer than 1,000 vectors, unique vectors in it, I think I never build it. It's not worth it. I don't need it. I can just do the binary search much quicker. And so whenever I do the lookup, I have a function called hyperhash lookup. It says, well, do I have a hyperhash? Oh, no. Okay, do the binary search. I don't need it. So you don't have to have it. I don't have to have it. But when I do need it, I need it badly. And I need it badly for the GPU, in fact, because binary searches are very costly on the GPU. A hyperhash is much faster on the GPU. And it's better on the CPU too, actually.
Is the hyperhash serialized?
Oh, in GRB serialized?
Yeah.
That is a good question. I think not. I think I discarded
And just rebuild it
and
if you need
rebuild
it.
it
Yeah.
because it's pretty quick to build.
Okay.
I think
Well,
I
that's good.
skipped
That compacts the storage for
Yeah,
Postgres.
I don't think I no, nope, it's not there.
And it's the storage requirements for the hyperhash are
Order
on the order of values, right?
of, well, no, of the matrix?
Yeah.
Oh no, it's tiny. It's order of the number of non-empty vectors in the matrix, which is n, less than n, right? So if I've got a hypersparse matrix that's 2 to the 60 by 2 to the 60 with a billion entries in it, but those billion entries are, say, a billion is a big number, but let's say E entries in it, but those E entries are in K non-empty vectors. The hyperhash data structure is order K in size. It's tiny.
Oh, right, because the values aren't in the hyperhash, just the indexes.
Right.
Right.
The values
Okay.
aren't there, just the names of the columns and the number of buckets I get to pick. So if I've got 10,000 vectors to hash into the hyperhash, I might give myself 40,000 buckets because I don't want to have many collisions. and each bucket holds an integer. So it's order four times the number of vectors. So it's very small.
Okay. Well, Peter, do you have any
So
questions for, or are we, you want to keep going?
let's see. Oh, for the hyper, I was going to show this is where I use the hyper hash where I touch it throughout the code. The Y matrix. It's inside the GraphBLAS matrix, and there's lots of. It's not used a lot, honestly. It's not needed in a lot of kernels.
But like you said, when you need it, you need it bad.
When you need it badly. I think it's called hyper hash lookup. Hyper hash lookup. Yeah, there we go. You can see this is where I'm looking up looking up the thing, and basically, if I don't have it, I have to do the binary search. If I do have it, it's much faster. I still might do a binary search, but it's reduced in size. If I have a super big bucket, which is rarely happens. Otherwise, I just do a linear time search, and so it's pretty fast. But this is the only places where I actually need it. Act-L hyper hash lookup. I mean, it appears in some assigned kernels, set element, EYs add, one of the EYs multiplies, extract, and SAXP3 and .3 matrix multiply, like in 6 different algorithms or so on that order. No, a little bit more than that, but not that many. Not that many. Because most of the time I go the other direction. This is the hyperhash lookup says given J, what's K? Well, the hyperlist has the opposite. The hyperlist AH has given K, look up the kth position, and that gives you J. So it's a function going from K to J. I already have that. That's easy. That's linear. That's constant time. J equals AH of K. The hyperhash does the inverse of that. Given J, where is it? And so many of the algorithms I have don't need to do that opposite direction. So they don't need the hyperhash. They're agnostic. They don't care about it. They don't access it. They don't care if it's there or not. But these algorithms, to the matrix multiply kernels, to the EYs methods, extract, you want to extract kernels, and zombie assignment. I'm assigning zombies. 4 of the zombie assigners. And that'll be later today when we go to the assigned kernels. So anyway, but the hyperhash build is in this folder as well because it's using builder. Now I could have put it in, and maybe I should move it. I don't know. Maybe it doesn't belong in builder. Maybe it belongs in the hyper folder. I have a folder called hyper, which does all sorts of interesting things with hypersparse matrices. Yep.
Cool. Well, I don't have any other questions. Peter, you got any questions?
I guess a clarification on when the matrix size actually makes its appearance.
The
So
dimensions?
yes, the dimensions, the main, and during the insertion, at some point you cannot check it because you don't know it yet, and then you know it. Is this
For builder, do you mean?
Yeah, for the builder.
Ah, okay. Okay, that's a good question. Yeah, because that actually doesn't come up. And let me explain why. Whenever you build a matrix, this is the user interface. So let's look at the include file actually. The build method you give it the output matrix already. So where's matrix build? So let's say you're building a float matrix. You call build or build FP32. You give it the matrix you're building, and it's not star C there. It's not a constructor. You give it the matrix of a given size and a given type, and that's the size of your output. You have to tell me how big it is via that input matrix. That's where it comes from.
Okay.
Yes, otherwise you'd have to pass it in potentially. Like, how big of a matrix do you want? What should the type of the matrix be? Well, I guess this would be float. If you have float values, maybe. But you could build with this function here, you could pass in float arrays, but this matrix could be of type double. And then I have to typecast. That's weird, but the size, so this does define the final type of the output. So there might be a final typecast at the very end of the day. But what's more common here, that's kind of weird. What's more common is that you've already allocated that matrix C, and that you've given me a place to put the built matrix. That place to put it, the output C matrix, since it's already allocated, with nothing in it, by the way, no entries in it, but the dimensions are defined, and it's defined that's how the dimensions are defined. In fact, it's kind of curious. The build could have been a constructor, right? It could have been it could have been a star C there. It could have said, "Oh, I'm going to actually give you the constructed output matrix." They decided not to do that when the spec committee designed this function. So as a result, then this tells me then not only what the type of the output matrix is and then I have typecast if need be, but it also tells me the dimensions of the matrix. I get it from the input output matrix. If the matrix has entries, I have to return an error code, which is kind of weird. Let's see, where is it? Yeah, here we go. There's an error code called GRB output not empty that says your output matrix does not start empty. What are you talking about? I have to have a place to put my tuples that I'm building. What do I do with the matrix? You give me that, you're supposed to give me the empty box to put them in, and it's not empty. That's what the spec says, which I think is a little bit overkill, honestly, this error condition. Because the very first thing I do is when I'm about to, like, oh, I'm going to obliterate the input matrix anyway. So just let me obliterate them. Why not? Just overwrite them. This doesn't free the matrix. But it frees the content, but it keeps things like type dimensions and some parameters like option settings. You can set a matrix like what formats can you be and that sort of thing. All that's preserved by this free function. So I free all the tuples. It free all the elements, all the entries in the matrix. So right now, if you look at the matrix, it'd be well, it wouldn't be valid. It has no content at all. So it actually is not just an empty matrix. It's worse than an empty matrix. But all the internal arrays are freed. So it's no longer valid. It won't be valid until the function finishes. But yeah, that's the error handling. It's kind of funky. So you have to give me the output matrix for me to build into. And you have to give me it such in a way that it's empty. If not, I have to report an error. And the very first thing is, thank you for this empty suitcase. Now I know the size of the suitcase. And now I'll throw away all the data structures in it because I'm going to replace it with mine anyway. Well, I could I could just throw away, if you give me a matrix that's got stuff in it, I'll throw it away for you. Oh, no, 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 no. You have to tell me that's an error. Okay. Whatever.
Is there
I
a
mean, it
situation,
could,
you mentioned C
go
is
ahead.
in this invalid state, it's sort of just this shell after you free the arrays.
It's once I free this array, yes, it's a shell and the magic is set. If I look at Fibix free, where is it? It's in matrix Fibix free. Yeah, it's a shell. It's just the header, and it's the 5 free declares it as magic. So its magic is now bad. GB5 free. I mean, this frees the P, H, and Y components. So it frees the P array, it frees the H array, and it frees the hyperhash, and it sets the magic to this is bad. And so I've got to stop here at noon.
Okay.
I've got
Yeah.
some,
Yeah, we can go.
but yeah, that's what so it's an invalid object. And if by chance something happens later on, like the builder runs out of memory, you were returned with an invalid matrix. You asked to try, you look at it and it'll say invalid object if you try to use it. So not only we run out of memory, C is now invalid. Tough luck.
All right. Well, I'll stop here.
So, yep, but that's the size of the matrix.